Okay, good morning. So today I will actually use the board and not use the slides, and I hope it will be okay and the pace will be comfortable. Okay, so today I want to discuss phase transitions in hardcore models still, but rigid straight rods on a lattice. Okay, so for simplicity, we will take a square lattice. And the particles will be rod-like, so they are rectangles. Of size 1 cross k. K is an integer. Let me draw size 4 here. So you can have a particle which is like this, and something else which is like this. Okay, so each particle is of size k. K is 4 in this picture, and they cannot overlap, and that's the only constraint. And then you have a given density of such rods which cover the what fraction of area we cover will be called the density, and we would like to determine the behavior of this system as a function of density, assuming that all allowed configurations are equally likely. Okay, so this problem has actually a long history. So I think I mentioned yesterday that the first geometrical phase transition is normally ascribed to Onsager, and he studied long cylindrical rods in a solution, and he showed that if the concentration of rods becomes large enough, then no external other parameter is required, and they become orientationally ordered, and you get a liquid which is anisotropic, or most of the needles are in some direction and not in other. And so this is a continuum model of cylinders, it was called, and he actually showed it in the limit of the rods becoming very long and their diameter being very small, such that the ratio of diameter to this tends to, so this is length b and diameter is d, and b squared d is equal to finite, and b goes to 0 and b goes to infinity. Yes, larger. Okay. So this limit sounds a little bit artificial and singular, but in this limit one can actually determine the exact equation of state, and it terminates after the second term. And that was the sort of point about his discussion, was to show that actually you can get a phase, but in practice D is not so small or B is not so big, and you can actually see things like tobacco mosaic virus, which are not conventional particles, but they have more or less the same size, and you can make solutions of them, and then you can actually see that above some concentration the solution becomes optically active, in the sense that it shows polarized light shows rotation. Okay, so it's easy to detect experimental system, and so in continuum these kinds of long cylinders undergo a phase transition. So then there was the question that can one see this phase transition in lattice models? And the lattice model was defined by Swansea, but it was not very clear that the lattice model also shows a phase transition. The point was that here, if you have a low density, then there are very few rods which are very far from each other. Each rod can be horizontal or vertical with roughly equal probability, and there is no orientational order. So it is clear that at low density, the phase is disordered. Is this size big enough? At low density, we have a disordered phase. Disordered phase. Yes. So these were cylinders which were actually symmetric and they were not optically active. But even in the disordered phase, they don't show the rotation of the polarization, and in the nematic phase, they show. Yeah, but I was looking for a macroscopic simple signature of the optical activity, and it's a more, I don't have to look in a microscope. I just do a macroscopic measurement and it works. You are not convinced. Same thing, yeah, cross polarizing. I'm just saying that it's a way to check that there is different behavior macroscopically, and that is a gross and simple test. Okay, so but suppose I increase the density, then would there be a density at which you can get orientational order amongst the rods? And this was not very clear, because if I consider the case of maximum packing density, in this case, you can actually cover the whole space with such rods with no empty space left. So that is density equal to 1 case. And in density equal to 1 case, it's not very clear that there is any orientational symmetry breaking. The reason is that, this is not a full-fledged argument, but so I take a big rectangle, square, and I break into small k by k squares. And in each square, I can put the rods either horizontal or vertical. And this I can do independently in each k by k square. So you have perfect packing and you don't have any orientational order. And the number of configurations is 2 to the power volume divided by k squared. So there are much more disordered configurations than there are ordered configurations. And so you don't expect this system to show orientational order at density 1. Okay, of course, these are not the all possible configurations. There are many more. But the orientationally ordered case, which you might expect is perfectly orientationally ordered, there are only 2 states, either all horizontal or all vertical. So it doesn't work. Okay, so we don't expect orientational order at full packing. And so it was not very clear that it occurs anywhere. In particular, if you take k equal to 2 dimer case, then there is a proof that dimers at any finite density of holes do not show any phase transition. That is an interesting proof. I mean, the proof is by Lieb. And what he shows is that the partition function of dimers does not show any singularity as a function of the density. However, there is a phase transition in dimers as a function of density. And that is the percolation transition. No, in all dimensions. If you take very low density, there is no percolation. If you take high enough density, there is percolation.
No, not that. Dimers do not phase separate. That statement is true only in 2 dimensions.
No, they're not phase separate. They don't show a phase transition. They don't show orientational order at full packing or at any packing. This much is true. But I'm saying that the entropy per site, which is the variable we can discuss here, does not show any singularity as a function of density. But you can actually define observables which will show a phase transition, which is there a spanning cluster? To define a spanning cluster, you need to define connections. So if we say that if a rod touches another rod, they belong to the same cluster, then there is a phase transition in the dimer model even. Okay. So anyway, so it was not very clear what happens in this case. Then the problem was left uncertain. In fact, there was a book written by Dijon on liquid crystals, and they say that it is not very clear that in the lattice model there is a phase transition. This is written in 1972. So, long time, 20, 30 years happened, but people couldn't decide what happens in this case. And yes. Yeah. So no, see, many of these things are obvious in hindsight. I'm only pointing out that in 1970, wise people like Dijon could not decide that there is a phase transition or not a phase transition in this model. Okay. Okay, so
not decide because there are these other quantities that show in spite of the
no, I don't know what he was thinking. So no, I have no idea. But they write in their book that it is not very clear that the lattice model undergoes a phase transition. Okay. And so now comes the question, so what actually happens? And we did some simulations with Anand Mohan Ghosh, this model, and we found that if you work with short rods, then nothing happens. But if the rods are long enough, then they actually undergo an orientational ordering transition. And then, what happens to this argument which says that, at density 1, the phase is disordered. So the answer is that there is a non-monotonic dependence of the orientational order on density. And there are actually two phase transitions. Initially, when you increase the density, the big thing becomes ordered. And then when you increase the density even more, it becomes disordered again. There are two phase transitions in this system, and that is what we will like to explore and understand. So, yeah. Just coming. Two phase transitions. So there is a, you can see nicer pictures in the published paper. This is 2006, Dhar and Ghosh. But the disordered phase looks like this. There are very widely separated rods and there is no order. At intermediate density, you get a phase like this. So there are orientationally, and a few rods vertical direction, but there is almost perfect orientational order. And then if you go to very high density, then you get a phase like this. Yeah. The width of the rod is 1 and the length of the rod is k. These are two-dimensional lattice models. So the yeah. The rods are the same rod, but I just increased their number. And there is a phase transition for rho less than rho 1. The status is like this. And there are some values rho 1 less than rho 2, where it is like this. And for high density, rho 2 close to 1, and there is a disordered high density phase. So this phase we will call rho is near 1, high density disordered phase. So we would like to understand how these phase transitions occur and what can we say about them. Okay.
Full-packing, I mean, even the ordered phase has some entropy.
You can make a partially ordered phase in which, you know, so the order parameter here is defined to be O is equal to number of vertical rods minus number of horizontal rods divided by number of vertical rods plus number of horizontal rods. This lies between -1 and +1, and you can take any value in between. And so perfectly ordered case is when all rods are horizontal or vertical. That has an entropy, but that entropy is sub-extensive, because once you start the rod, then you just have to place everything in parallel. So the entropy goes as root L. So that is only root L. Okay. So this is the order parameter we will use. And the order parameter as a function of density seems to be something like this.
Deepak?
Yes, just a minute. Yes.
So on the third diagram where rho 2 is close to 1, there are some clusters where they are pointing all upwards, and then
Locally, there is a local square kind of ordering. So the structure looks roughly like what I drew here, but these are not perfectly synchronized, and you know, these there is some, you know, one sub 4 by k rods will be parallel, but they will not be in synchrony with the next.
So there's no typical size to these local clusters, as in as a rho minus rho 2 to the power. I mean, I don't know something.
Well, we don't know. You know, I'm just going along, and this is what we see, and this is sort of the structure of the phases. So the low density phase transition from the disordered phase to the nematic ordered phase has been studied. You know, you can study it by Monte Carlo. That's all we can do. We cannot do analytical studies on this. And it turns out that it seems to be in the Ising universality class. That seems quite reasonable, because there are two ordered states. One is vertical, one is horizontal, and there is a disordered state. And if you coarse grain the system, it will be, you know, so some system which has some disordered state, some plus state, some minus state. And so it looks like an Ising model with some interaction between neighboring stuff wants to be parallel. And so it will be in the Ising universality class. And that is actually verified in Monte Carlo simulations. So the first phase transition, we will say we understand, and it's in the Ising universality class. If you take some other lattice like the triangular lattice and do the same problem, then you have rods with 3 orientations possible. And then it's in the Q equal to 3 parts model universality class, not Ising. Okay. And I guess if you work in 3D, some such thing can also be done in 3D. Rho 1 depends on K. That is actually easy to guess. It goes like 1 by K. No. I will give the argument for the benefit of everybody else. So what happens is that what matters here, if you look at this picture, is the areal density of rods, but measured in units of, if I take a K by K square, how many rods are there inside it? And maybe the rods are not fully inside, but they are. So what is the average occupancy of a K by K square? That kind of decides if it is high density or low density. So if you say there is a continuum limit of this model where K goes to infinity, that model will be just lines on a continuum. Okay. And in that problem, it is clear that, you know, you should take the length of the line to be 1 and see what is the density of lines per unit area, which is determines the, so rho C will be some number in this continuum units. So rho 1 goes like A by K for large K. And we found numerically that this A is around 6. Okay. And so if you put k equal to 5, then rho 1 becomes bigger than 1. You don't get a phase transition. But if rho 1 is 7, then you actually have a first phase transition to a nematic phase. So for all k bigger than some value k1, there is a phase transition to a nematic state. Okay. But now there must be a second phase transition to the high density disordered phase. And this phase transition is much more tougher to understand. And that is what we would like to discuss today. Because, okay, so if you take a triangular lattice and do the same construction, then there are 3 orientations of rods, and there are 3 ordered states, 3 nematic ordered states. And so in coarse graining, it will become Q equal to 3 parts model. And so it will be in the Q equal to 3 universality class. Okay, so now I want to discuss the second phase transition. No. Okay, so what we would like to show you in this lecture today is that the second phase transition is a first order transition. And for me, it is convenient to work with a variable which is the density of holes, which is 1 minus rho. And so in the first order phase transition, there is a 2-phase region. Epsilon 1, epsilon 2, where you see a phase separation. The system will separate into one part with density epsilon 1, one part with density epsilon 2. And if the epsilon is less than epsilon 2, then you have a uniform phase with some density of holes. Okay, so we will like to argue that epsilon 1 log k divided by k squared sorry, wrong way. And mu star so in the limit of large k, you can actually determine, show that this phase transition is first order, and you can determine the coefficient, what is the activity at which the phase, this is the chemical potential at which the phase transition occurs. And it's interesting that one can actually show the coefficients of this. There is a log k by k squared dependence, but usually it's hard to determine the coefficient. But here you can determine the coefficient, and it is 1, which is a simple number. Yes, sir. So I should be careful, and I should actually draw something like this. Actually, no, because this is not a phase diagram. This is just the order parameter. So the order parameter goes to 0, and there is a jump here. Yeah. Okay. Okay, so this is what we will like to show. And I will also show that this result holds exactly like this in all dimensions. Even d equal to 3, 4, 5, you get exactly same result with exactly same coefficients. This one says epsilon 2 goes to 0 faster than any power of k.
So there's a 2-phase.
Yeah.
Region.
Yeah.
That doesn't quite jive.
Why not? So that is why I said I was sloppy. If you have row less than row 2 left, and this is row 2 right. So there is a two-phase region, left and right are not coincident. And there is a region in which there is a unique state, and there is a region where there is phase coexistence. Okay, very good. So now I want to establish these results. No, there is a region with density of holes equal to epsilon 1 and density of holes equal to epsilon 2. And okay. So in order to establish this result, we actually need something else before. We need to determine what exactly is the entropy of this dimer problem at full packing. If you take this k/1 dimers on the square lattice, so this is defined like this. Sk is equal to log so I take a KL by KL lattice. It can be fully covered with k-mers. And I find out the number of ways you can cover a finite rectangle of this size with k-mers. Take the log, divide by KL squared, which is the, actually I will prefer to do this with k squared L squared. So this is the number of sites in the lattice, and this is the entropy per site at full packing. Okay, so the definition is clear, and we will show that Sk times k squared by log k, limit k goes to infinity, is also 1. Okay. And so because these results can be established, they are kind of interest. And the way one gets at them is also of some use. So first I will establish the result for d equal to 2, and then we will generalize to higher d. So d equal to 2. So what I will do is I will establish tight upper and lower bounds on Sk. So we gave some lower bound on Sk here. It says Sk is greater than equal to log 2 by k squared. You just have to divide this here. Okay, but turns out that there is a stronger bound which says what is goes like this, that you construct a long stripe of width k and length L and cover this stripe with k-mers fully and find out how many ways you can do this. And then if you have a big lattice, you just cover it independently in each of the stripes. And that certainly gives me a lower bound on the full number of covers. Okay. So what is the number of ways I can cover this thing with fully with k-mers? One thing is that I can start something with the vertical k-mer, then the problem reduces to L-1 size. The other thing is that no, you don't put this vertical. This has to be covered, so it is covered horizontally. But it is covered horizontally, then the next one you cannot cover vertically. It's not possible. It goes out of the strip. So you have to cover it with k horizontal rods fully. And then the problem reduces to L-k. So I have a construction, in this construction, NL is equal to NL-1 plus NL-k. And so if you say that NL goes like lambda to the power L, then lambda satisfies the equation lambda to the power k is equal to lambda to the power k minus 1 plus 1. So that gives you the entropy per site is just log lambda divided by k. Okay. So now if k is large, then this lambda is very close to 1. And we can try to determine its behavior. This is of some interest because we are going to study large scale limit. So I want to do this elementary exercise in some detail. I want to determine what is the solution of this equation. This is a polynomial equation, so it has k solutions. But we will look at the solution which is the largest modulus or the largest positive real solution. Okay, and so then let me say that I make a guess that lambda is equal to a by k, 1 plus a by k. Or you can make the substitution in this equation. Then for large k, lambda to the power k is approximately equal to 1 plus a by k to the power k. So for large k, this is e to the power a. Okay, so here you put this equation is lambda to the power k minus 1 into lambda minus 1 is equal to 1. So it becomes e to the power a equal to k. To leading order in k. To leading order. Now this equation is a well-known equation. It's called the Lambert equation. But for the students, let me just say that, so you can just take this here and you say a is equal to log k by a. And so that is the leading behavior is a goes like log k. And then, so if you put this in, it goes like log k minus log k to next order, but I iterate again, and then it will be log k, and it never stops. You just keep on getting more logs one after another. So if I want to do asymptotic study of this for large k, this is not very comfortable. It is actually very irritating because you don't get rid of the logs. You don't go to any term higher order in 1 by k. You just keep on getting stuck with logs. So the way out of this is to say exactly this, that A is a solution. So I will say lambda is equal to 1 plus a by k plus order 1 by k squared, where actually let me say small o and order 1 by k squared, where e to the power a is equal to k. So I say a is the solution of this Lambert equation. All the logs inside are buried in a, and then whatever is the correction after that is 1 by k, in lower order in 1 by k in power. Okay. Actually, we don't need this, but one just realizes that you have to be careful in taking the large scale limit. It is not going to be trivial. Yeah. E to the power a. So here, this equation has been rewritten here. It's the same equation. You can determine a. Lambda to the power minus 1 goes to 1 by a by k, which is 0. So this equation is rewritten here. This goes to e to the power a, this goes to 1 a by k. It goes to 0. So one part goes to infinity, a to the power. Sorry, I said it wrong. This equation is correct as written here. As okay, A goes like log k, so it goes to infinity as k goes to infinity. It goes very slowly, but it goes to infinity as k goes to infinity. E to the power a goes to infinity, and the next term goes to 0, and the product remains 1. Okay, very good. So now I have established this lower bound where, so I get that entropy Sk is less than equal to log k by k squared plus lower order terms. Okay. Lower order in log k. Log k is included in the lower order terms. Okay. But now there is actually an existing result which is very non-trivial. Sorry. This one? Oh, I beg your pardon. It is the wrong way. Yeah. So there is an upper bound by Piaget and Gagunashvili, who showed that Sk is strictly less than equal to log 2k by k squared. So to leading order in k, both bounds are the same, and the coefficient a is exactly 1. That's the end of this proof. How did Piaget and Gagunashvili arrive at this result? I will not give you the full proof. In fact, I don't have it with me, because this paper is published in some Russian language and in some obscure place. I even got the translation done. But the Russian people used to write in very telegraphic style. So it's a short 1.5 page paper. They don't give any argument. They just say, we can show this. And you have to reconstruct the argument on your own, which one can try to do. But I will not give that proof here. But I'll give you the argument. So what they say is that you take a k by k square. Sorry, kl by kl square. And then you divide it into k by k subsquares like this. And you consider the top left cell in each of these. Okay. So there are L squared of those. Each of these cells is covered fully. We have just agreed. So how many ways can this cell be covered? This cell can be covered in 2k ways, because it can be covered horizontally, but there are k ways of covering it horizontally by sliding. And there are k ways of covering it vertically. So there are 2k ways per cell. So there are 2k ways per cell you can assign covering to each of these. And then you can see if there is a covering of the full space consistent with this. And what they argued is that at most one covering for a given assignment of covering of the marked cells. So there are 2k ways of this. So omega is less than equal to 2k to the power L squared. And so, then you just get the bound immediately. The proof of this, I will just give an intuitive notion, is like this, that suppose I try to do this using transfer matrix. So I will say that I actually know the ways you can cover this part and this part here. And then I try to cover the rest. And I also know how to cover this. Then within this square, there is only at most one covering possible and no more. So then iteratively the proof goes through. There is a little bit of subtlety involved with the boundary condition that I will not discuss. But it's a technical detail. Okay, so we have got this result that S of k squared rho equal to 1 divided by log k equal to 1, limit k goes to infinity. Okay. And now I would like to argue that this result actually holds in all dimensions. Okay. So in higher D, what happens? So the argument is actually not rigorous, but it is perturbative. But you know what this says is that it is convincing for a reasonable person, but not for an obstinate person. Okay, so let me give the argument. The argument is like this, that if you, so Sk rho equal to 1, D equal to 3. This is what we want to determine. And this is greater than equal to Sk rho equal to 1, D equal to 2. The point is that you can just take the three-dimensional space, cover it slab by slab. In each slab, you can cover it with scale D equal to 2 ways, and then you have more. So how much more do you have? So now let me determine Sk rho equal to 1, D equal to 3 minus Sk rho equal to 1, D equal to 2. And I will like to argue that this goes like 1 upon k to the power k. So to low order or any order in k, it doesn't matter. The correction is very small. So, asymptotic results are unchanged. What is the proof? Well, I can take the unperturbed state as a covering by horizontal two-dimensional rods, and I want to cover 3. So then I need to put in some vertical rods in place. How many ways can I put in vertical rods? So maybe I put in 1 vertical rod. That won't work. You have to put in at least k vertical rods in order for the system to be fully covered, because in each layer you have to have full covering. There should be k holes at the very least. Okay. So now if you try to put in k vertical rods adjacent to each other vertically, if originally there were k rods for all horizontal, now you can make them all vertical, right? So there is some way, but suppose you pick on the ground floor some horizontal rod, then the next layer is going to be exactly on top of this, only in small cases, 1 upon 2k ways, and then the next one should be on top and so on. So the answer is 1 upon 2k to the power k minus 1. To this order. Now there are other configurations in which they are not exactly on top, but they are slightly further away. But you can convince yourself that order by order, this argument is actually good. But whether the series sums up to finite value, we will not show. But it seems plausible that this result, as stated, is good. So here I should say order. And then it says that in all D you get the same result for large K. Okay, the entropy is actually D equal to 3 is actually bigger than D equal to 2, but by a very small amount which goes to 0 as K becomes bigger. Okay, so now I want to work at finite Z. So not full packing, but not full packing. And yeah. Yes, so actually this is observed also in Monte Carlo, that at high density in more than 2 dimensions, you get a layered order. The rods horizontal order in a layered format, not nematically. And so what happens is that the rods separate into layers. The layers are more or less independent. And then whatever phase transition happens as a function of density occurs within each layer. And the fact that you are in D equal to 3 or 4 or 5 doesn't seem to matter. And you get exactly the phase transition. It is driven by the d equal to 2 transition. So we need to study only the d equal to 2 case, and the others are not modified. Yes, it is a symmetric is layered, so it is symmetric. Within the layer, there is no crystalline order. It's a layered, but okay, let's not use the word symmetric, let's use the word layered. So it's layered almost perfectly. Most of the rods will be within a plane and not across planes. Okay, and this fraction which are not in the plane goes like 1 upon k to the power k. Okay, so yes, 2D layered. Even in 5D, their layering is 2D. You can cover a 5D hypersurface with 2D layers, and each layer you cover with the rods as in 2D, and then make up the system by a set of layers of this toy. Huh? Yeah. 2D layering with very few rods of different orientation. Okay. Okay. So now we want to study this. So the clue for the answer comes from the fact that what we observed in simulations is that in the nematic phase, the nematic ordering is pretty close to perfect. So a good starting point for the nematic ordering is to take the case where the ordering is perfect. You say all rods are horizontal. I beg your pardon. And how many ways can I fill a big square with all rods horizontal? There is a finite entropy. Can we determine it? This problem is very easy because the rods, different lines along the 2D plane become decoupled with each other because all horizontal rods don't care about the next layer. So the problem reduces to a one-dimensional problem. And so the problem is like this. I take omega 1d of z is, you take a rod of long system of size L, and this is 1dl, and the partition function is equal to sum over all configurations in R, L, z to the power r. That's the definition of the partition function. And NRL is the number of ways you can put R rods on this, and sum over everything. And log omega z divided by LK is equal to lambda. Sorry, I like to call it omega L raised to the power 1 by LK limit L goes to infinity is called partition function per site, and it's a function of z. Okay, but finding this lambda z is a 1D problem. You can solve the problem in 1D and then just multiply as many layers as there are. So for the 1D problem, if you have a rod of length L, will be either the left end will be empty or it will be covered with a rod. If it is covered with a rod, then the remaining stuff is L minus K. If it is not covered, it is L minus 1. So you get that this omega L is equal to omega L minus 1 plus Z omega L minus K, which is very similar to the other recursion we wrote. And so so if you get this lambda to the power K is equal to lambda to the power K minus 1 plus Z. And this then determines the partition function per site for the fully ordered case. So I'll call it lambda nematic. It is fully nematic ordering. Okay. But now I want to study the case with it's not fully ordered. But again, what I can do is I can start with the fully ordered state and try to put in vertical rods now. So I do perturbation theory in the number of in the activity of rods in the vertical direction. And so I will write omega of KL by KL. And this is, I will write Z horizontal, Z vertical for two different activities, which will be omega KL cross KL, Z horizontal 0. Put Z vertical equal to 0, then this is a easily calculated quantity, and I would like to write this as 1 plus ZV plus ZV squared plus ZV cubed, expansion like that. And the coefficient of all these terms, you have to evaluate by counting the number of ways you can put in one vertical rod, two rods, three rods. And it's easy calculation, order by order. It's a standard perturbation theory. And what I find is the coefficient of ZV is number of sides multiplied by epsilon to the power k, where epsilon is the density of holes. Because, you know, if I have this big stuff and I want to put a vertical rod, then originally it should have been empty. And it's empty with probability epsilon and then epsilon to the power k. So for a fixed finite epsilon, each term in this expansion goes to 0 exponentially fast as k becomes large. And so the ordering is nearly the same as this ordering and the corrections are small. Okay, so then, I have this sort of problem which I wanted to determine S of rho as a function of rho. For very small rho, this is rho log 2 rho. So, you know, the entropy increases with rho almost linearly, but with this coefficient. And for large density, it tends to some value, which is finite. But I have a bound on it, which goes like this. This is the S-nematic. S-nematic is more or less similar to this, but it differs by a factor rho log 2. So it is below. Okay, and yeah. So now I have to reconcile the fact that the actual function is like this. And how do I do this? So the answer is that we know that the actual entropy function is convex. And it goes to a non-zero value at rho equal to 1. It goes to this value. So now, by tangent construction of Maxwell, you can draw a graph like this. And this region in rho nematic is no longer allowed. Because if you take a density in this region, you can actually break the system into one phase with density equal to, so this I will call epsilon 1, and another density 1. The density 1 can be covered in finite entropy and the other one can be covered. And you know, the full entropy is more than what you would have got by taking nematic order with this uniform rho. Okay, so very good. So this construction is simple. In fact, I have a result like this. This graph was not drawn very carefully. There is a regime, which is the nematic regime, where the actual density is very close to the fully ordered nematic for large k. The corrections are only exponential minus k. For k large, they can be made as small as you please. So in this intermediate regime where there is nematic order for large k, the full S rho coincides with rho S nematic, and then it breaks away from it. And in the low density regime also, it doesn't coincide fully. because there is a log 2 extra, then you get some extra entropy because of the orientational degree of freedom per rod. Okay, but now I know this break here. I know the equation of S-nematic. Okay, so I can actually determine the tangent. So this is the tangent construction. And you can determine the point where this tangent from this end will touch the curve S-nematic, and you get this result. Epsilon 1 is approximately log k by k squared. And in this construction, the second value is actually at rho equal to 1. But if you actually take a system at finite activity, then it seems reasonable that it cannot be fully covered. The high density phase will not be fully covered. There will be holes with finite probability. And so rho 2 will actually not be 1, but within this approximation, it turns out to be 0. And if you do an improved approximation, the epsilon 2 comes out to be exponential minus k. So this construction is pretty good, not exact. And the slope of this curve gives you the chemical potential at the transition, which is k log k. And epsilon 2 is exponential minus k of this, maybe only one wiggle. Okay, so I think I will stop here. There is some more stuff, but you can read it from the paper published. And we have shown that order by order, you can take care of the holes a little bit, because this argument, in the high density phase, it's not working very well. But you can show that the hole density is small. Then consistently, this argument shows that there is a phase separation into two phases, one with epsilon 2 and one with epsilon 1, and epsilon 2 is only exponential minus k. Okay, so let me stop here and I can take some questions.
We had many questions, so we can still have some time for if there are still questions left.
Yeah.
To how it goes to 0, like 1 by log k, there's some log correction, there is no.
We can show that order by order it goes like e to the power minus k, but with some coefficient which you can determine approximately, not exactly.
Okay.
We take care of some terms and it's exponential with some coefficient. You take care of more terms, it's still exponential, but with a smaller coefficient.
Okay. So it's not even log 1, like it's even faster than 1 by log or something.
No, it is exponential in k. So
Okay,
that is what I wrote here.
Yeah.
This one.
Yeah, exactly.
So it goes faster to 0 than any power of k or any. Yeah.
But it can go to like even faster than log k to the power this thing.
Yeah, it goes faster than any power. It goes like exponential minus k more or less, but we cannot prove this.
Okay.
But we can certainly say faster than 1 upon k to the power 10 or some such thing.
So, I mean, in the simulation, like if you put k equal to 10, I mean, so these are pretty small, right? Epsilon. So, I mean, how well can you?
So what we have been able to do is to take a k by infinity strip, and with finite density of rods, you cover it, and you calculate s of rho as a function of rho, and it sort of goes like this. Sorry. Not go near rho equal to 0, but rho equal to 1. There is a sort of a jump, but this jump, because this is working on a finite strip, is actually rounded off, but rounded off to 1 part in 1,000 for k equal to 10. And so, we expect that if you work with bigger strips, this will actually become a discontinuity. But with finite strips, you don't see exact discontinuity, you only see rounded off discontinuity. So S of rho is convex, but as a function of Z. Sorry, as a function of rho. Just 1 second. Maybe I didn't draw this very well. Yeah, so this is nematic order parameter.
That's fine.
I beg your pardon. Yeah, so the
Good, thank
first
you.
order jump occurs in the nematic order parameter.
I had trouble sleeping last night.
Sorry?
I had trouble sleeping last night because of lack of convexity.
No. So this one is okay. Sorry, I was looking at the clock too much and not paying attention to what I'm saying.
Deepak, you also have some hard plates model.
Ah.
So if I have hard plates in 3 dimensions, is it like these rods in 2 dimensions?
Okay, so we have discussed 1 by k rods, but you can also discuss m by k rods with k goes to infinity, m remaining finite. And most of the discussion goes through, there is no problem, but we have not worked out all the details. I mean, it is clear that the discussion will go through qualitatively, but then all these coefficients will become functions of m. And those we have not discussed. And there is a possibility that if you have m not equal to 1, there are additional phase transitions. So the situation may become more complicated, and that we have not analyzed in great detail yet. I forgot, I think, to mention that this work was done with Agam Shah, who is a student, was a student at IISER, and Rajesh. Rajesh at IMSC, and you can look it up in archives in the last 2 years.
Okay.
Yeah.
It's an old question I asked you before. In many real systems, in greater than 2D, mostly 3D, there is sometimes a sequence observed, which is isotropic, nematic, smectic, nematic again. So there it seems that in order to get a reentrant nematic, but nevertheless the order parameter is still nematic, the smectic order parameter is gone. So is this some kind of a general phenomenon that can happen, that for better packing, you will end up with a loss of translational order in terms of enhanced orientation?
I still don't have any satisfactory answer to this question. For this simple case we have discussed, there are only these 3 phases. The intermediate density phase, high density phase, low density phase, and nothing else. But what happens in more general cases, in higher dimensions, the arguments are sort of not fully convincing, but plausible. So, you know, some strange type of new ordering may possibly occur, but not in these very simple models. If you have rods with extra interaction, then you can have a solid phase. You can have a partial, you know, the kinds of stuff I mentioned yesterday, plastics, partially ordered solid phases and all that kind of stuff. But in these simple cases, it doesn't occur.
Thank Deepak for a wonderful detailed lecture.
There was some question from here. Yeah, here. Who said?
No, it was just a very little question. So this is for the large K limit.
Yeah.
And you said that K equal to 6 is a kind of critical.
K equal to 6, K equal to 7, you start seeing a transition. But the asymptotic results will not be valid for K equal to 10 even, but
Yes.
around 20, they become very good.
Okay. So have you analyzed the finite K behavior?
No, so these are first order transitions. So yeah, the coefficients will show some dependence on K, but you know, K is an integer. So I cannot look for analytic functions. You can just say K equal to 7 is this, K equal to A is this, and asymptotics can only be discussed for large K.
Our next speaker is Anupam Kundu from ICTS.